Okay, we're going to be talking about the experiment 18, air column resonance, the speed of sound in air. You're not going to find this in the Brightwave um, book. This is one that you'll find on Canvas. Go to Canvas and you can download the experiment from there. Let me share the iPad with you so that you can see what we're talking about. And so this is air column resonance, the speed of sound in air. This is, we're going to be working with a resonance tube. And this is a picture of the resonance tube. You can see I have a tuning fork here, right at the opening of this resonance tube. And this plunger, it's a little cork-lined disc on a little dowel rod. This plunger can be moved in and out until we find the resonance. The ones they show you in the book are the ones we used to use, but we won't be using that. We'll be using this plunger. It's a lot safer. The ones that we used to use were glass. A few of them broke if they were tipped over, but the concept is the same and it works the same. Okay, so as usual, you have to do the advanced study assignment. You read the text and you'll get most of the answers to the advanced study assignment. I want you to read the experiment. I'll read. I have a few sections highlighted here. In red, it says, when a system is driven at a natural frequency, we say that the system is in resonance with the driving source and refer to the particular frequency at which this occurs as a resonance frequency. So what we're going to do is we're going to find multiple resonance frequencies actually multiple modes of the same resonant frequency in these tubes. And I'll have a little demonstration. I'll follow this up with a little demonstration. So go through the theory and you can see that you have a tuning fork over the resonance tube. You get this, if there's only one if it's at the fundamental, you only have a quarter wavelength established in the tube. If you go to a higher frequency for the same length tube, you can get like a 3/4 lambda or 5/4 lambda, 7/4 lambda. There'll be odd multiples when it's a tube with a bottom on it. And in the case as shown here, these two young ladies they're holding here's the cylinder, the graduated cylinder, and this is it's a container of water hooked up with a tube. I'm sorry, this is the cylinder, and this is the container with the tube. As you raise it and lower it, you'll raise the water level in the tube and change the where it resonates at. Okay, let's see. So for this, so here it says the length of an air column will be varied. It used to say it does say by raising and lowering the water level in a tube. We're not using that. We're using by use of a plunger. We're using a plunger to change it. Okay, let's look here. You measure the inside diameter of the tube with the vernier caliper and record in the data table along with the room temperature. Now we're going to assume a room temperature of 25 degrees. I don't think I actually read the room temperature in the day I performed the experiment, but from having worked in that lab for many years, 25 degrees is a pretty average room temperature for that. And I also want to go up here, this highlighted. So a fork has directional sound propagation characteristics. You know, it's what that's saying is, if you look and see how I have the the fork, the tines, I want the tines going this way, or the tines are going to go that way, and I want the one of the arms disturbing the air molecules in the tube. If I were to turn it 90 degrees where they're going like this, it wouldn't be as an intense a resonance in the tube. So that's what that other yellow highlight is. Let's see. And so here I have the temperature is 25 degrees C in the room. We're going to assume that's a pretty good assumption. And the inside diameter of the tube is 21 21.7 millimeters, 0.0217 meters, and that's going to be used for one of the optional portions. You're welcome to try it. It's not that difficult. And this is the data table that you'll fill out. After this introduction, I'm going to do a little sample using a simulator, but so I can show you what to do without doing the work for you. I want you to go through and do the work. And then you answer the questions at the end, and that'll be you just turn in that experiment. And so this is really the only data table that you're gonna fill in. So in this last part, you're gonna calculate the frequency of a unknown tuning fork. So we'll end this here, and then I'm going to do a little demo with a simulator that shows you how we're going to how to fill out this table, because I've had a lot of students get confused. I may have contributed to that confusion in the way I lectured the last time, so I'm redoing the lecture this time. Okay, that's it for this one.